Welcome to Math Media. We see about Lagrange's theorem. We'll prove what's the statement of Lagrange's theorem. G is a finite group with order of G is equal to n, and H is a subgroup of G. Then we have to prove that the order of H divides the order of G. What is order of G or what is order of H? Order of G means number of elements in G. Order of H means number of elements in H. Therefore, the number of elements in H divides the number of elements in G. To prove this, we need three lemmas. First, we see lemma 1. Let G be a group and H be a subgroup of G. Then we have to prove the four results. A in H implies AH is equal to H, and AH is equal to BH implies A inverse B in H. A in BH implies A inverse in HB inverse. A in BH implies AH is equal to BH. Therefore, we prove the first case. First, you take A is an element of H, which implies A inverse is an element of H. We have to prove A is equal to H. There are two cases. One is AH is a subset of H and H is a subset of AH. Therefore, you take X as an element of AH and then X equal to AH, where H is H. Therefore, AH in H, since A in H. Therefore, we prove that AH is a subset of H. Then we have to prove that H is a subset of AH. For that, you take an element X as an element of H. We know that X can be written as EX since E is the identity element, and E can be written as A into A inverse. Therefore, X equal to A inverse X. A inverse in H and X in H, which implies A inverse X in H. Therefore, X in AH. If H is a subset of AH and H is equal to AH. Then next we prove this result. You take AH equal to BH and pre-multiply A inverse on both sides. Then following these steps, you will get H is equal to A inverse BH. Then using the previous section, we can say that A inverse B in H. Then we proved it. Then third one, A in BH you take and follow this method. Then we prove that A inverse in HB inverse. Then the fourth one, A in BH, then we have to prove that AH is equal to BH. Therefore, we have to prove two cases. AH is a subset of BH and BH is a subset of AH. Therefore, AH is a subset of BH means we follow this method and we prove that AH is equal to BH. And this is another section, another next case, we prove this way. Then we prove that AH is equal to BH. Then lemma 2. Let H be a subgroup of G, then we have to prove three things. Any left cosets of H are either identical or disjoint. Union of all left cosets of H is G, and number of elements in any left coset same as the number of elements in H. Therefore, let AH and BH be any two left cosets. Suppose they are disjoint, then we proved. If it is not disjoint, then there is an element in that intersection, and then you can say that AH is equal to BH. Therefore, any two left cosets are either identical or disjoint. Then you know that AH, if you consider the left coset AH, A in AH, similarly for every element of G, it's in its left cosets. Therefore, G is nothing but the union of all left cosets. Then we have to prove the number of elements in any left coset is same as number of elements in H. Therefore, we define the mapping F from H to AH by F of H is equal to AH, and we prove bijection means then it is okay. Therefore, first we'll prove bijection. For that, you take an element H1 and H2 are the elements of the domain. Then you may equate F of H1 is equal to F of H2. Then we prove that H1 is equal to H2. Similarly, you take AH is an element of left coset. Then A inverse AH is in H, which is the pre-image. Therefore, F is on to F is a bijection. Therefore, every left coset has the same number of elements as H. Then the third one, first you take the H as subgroup, the number of left cosets of H is same as the number of right cosets of H. Therefore, L and R denotes the set of all left and right cosets of H. We define a mapping F from L to R by F of AH is equal to HA inverse. First, we prove F is well defined. To prove well defined, you equate two elements in the domain. Then we prove that this is nothing but the its images, they are equal, elements are equal in the domain and the images are equal in the codomain, therefore it is well defined. Then one we can follow this method, and on to also we can use this. H is an element of R and A inverse H is the pre-image of HA. Therefore, number of left cosets same as the number of right coset. Then coming to the main proof, proof of the main theorem. G is the finite group and order of G is equal to n, and H is a subgroup and order of H is equal to m. Now we know that the index is R. Index is nothing but the number of distinct left cosets of H and G. Using that, we can prove that we know that order of G is equal to index into order of H, which implies order of H divides order of G. This is the Lagrange's main theorem. Have a great learning.